Then let's slowly start. And hi and welcome to the session of how to craft bulletproof Java enterprise applications for the hard production life. I'm very happy to be here and to be back in Istanbul. This is my second time, and I'm very happy to speak here at Java Day. My name is Sebastian Daschner, born and raised in Germany, and I work for this company called IBM. And in this session I want to show you as enterprise developers what we need to be aware of when we run enterprise applications in production. Because it's one thing to simply use APIs and build something up and implement your business logic, but if you run in production, then you might take a few things into consideration, especially if you build distributed systems and have a lot of communication going on. So what I'm gonna want to show is I want to show a lot of code and a lot of live demos as much as possible, but I also want to show you some resiliency principles, so what it means to be bulletproof and resilient in production. And for that reason I brought some example application. And if you know me, then you might know Kahveci severim. So I have some coffee shop example for you, and this is what I want to show you. So I have an example of two Java enterprise applications that I run that communicate with each other. The first one is called Coffee Shop, and the second is called Barista. So if you want to order a coffee, you go to the Coffee Shop application and communicate with it using HTTP, for example. And in our cluster, in our distributed in a synchronous approach for our case. So I actually already deployed that locally. So if I go to my local host and ask for some coffee orders, so this uses curl on the command line, so I can ask something with HTTP. Then this will give me a list of coffee orders, which is now empty JSON array, and if I want to change that, I can order some coffee. And I want to quickly walk you through the code, how that looks like, so you get an idea. Who of you is familiar with Java EE and JAX-RS? Hands up. JAX-RS developers somewhere have seen this app path annotation before. Who of you uses Spring and Spring REST controllers? Okay, roughly same amount of people. REST controllers are very similar from the programming model. So if you know REST controllers, you probably might be familiar with that. So what I want to show you, you can get a list of coffee orders. This is what we talk about, coffee orders. You can return the list if you fire up an HTTP GET request. This is what I just did. And you can order a new coffee if you post something to that resource, to that URL, right? So if you want to post a coffee order using JSON, for example, I can order some new coffee. So let's do this. If I go back to this URL and say, if I would like to post something, for example, post a JSON object to this resource, and that object looks, for example, as follows. I can specify the coffee type, the drink type that I want to have, that I want to order. In this case, I want to order an espresso or a Turkish coffee or a cappuccino, whatever you'd like to have. And I post this against that URL, and then it says 2 for no content. Okay, great. That's good news. And then apparently the coffee is in our system. So if I then ask again for this coffee, please give me back this coffee. Okay, now it's there. Okay, that's great. And when I tell you the first system communicates with the other, then this will be a synchronous call, and this will be a synchronous HTTP call. And that's already one thing we might take into consideration. So I briefly want to walk through this code logic here. If we want to order some coffee, then this doesn't do much. This coffee shop class has mostly one dependency here, the barista. That is a gateway to the other application that does this synchronous HTTP call. So you might have seen something like this. In Spring, it looks very similar with REST templates that you use. This is JAX-RS client. What you do a synchronous HTTP call to the other system, to the barista system. And that is already that can be a little bit dangerous if you do it like this out of the box. Why? Because we don't regard timeouts, right? If you do any external communication, be it HTTP or be it database connections, if you do a synchronous call, you have to regard timeouts, right? Why? Because, well, you call it synchronously and the whole thing blocks until it returns. But what happens if the external system is not available? So for example, what I'm running here locally is two applications, the coffee shop and the barista application. And as you can see in the code, the first one, the coffee shop, synchronously calls the barista application. And what happens if that becomes unavailable? Well, let's find out. But probably it's let me post something. So if, for example, I would now stop the second application, the barista application, then for this example, as you can see, now it's stalled, right? Because you don't know out of the box, if you write the code like this, which timeout behavior you have. And then depending on the HTTP client, there are actually HTTP clients out there that block infinitely, which is a bad idea, right? Because then your thread is blocked. And if you have a Java EE threading model, then you have, or with Spring is the same, you have a bunch of threads in your pool, but then ultimately if you have multiple calls like that, then all of them are blocked, and then your application basically is stalled and you can restart your server. So instead of doing that, what we can do with the JAX REST client example, we can use this builder approach and then basically specify some timeouts. Just for the example, I specify connect timeout and read timeout. Let's say 3 seconds each, depending on what your application is doing and what your network setup looks like. And then we can build up the same thing by specifying these timeouts explicitly. So that's one thing we might take into consideration. Another thing that I want to show you is microprofile fault tolerance. So I'm going to show you a few resiliency concepts such as timeouts. And microprofile fault tolerance, what it is, microprofile is an extension to Java Enterprise. Well, not only, actually you can also write plain microprofile applications. That initiative was started with the idea to advance Java Enterprise a little bit faster, besides being only standard technology. But it builds upon the Java Enterprise standards, so what we can do, we can use the same programming model, the same concepts, the same declarative approaches of specifying behavior with annotations by introducing some more resiliency concepts. So for example, what we can do also on a code level, if we include microprofile fault tolerance, we can specify some @timeout annotation, and that value has a value of 1 seconds, for example, and that specifies a timeout behavior on a code level. So if, for example, you're not only, for some reason, depends whether that makes sense, not only want to specify a timeout on a connection, but on anything that's now being executed here, you can do this using that annotation, and then it will throw an exception in case it takes longer. Question is, of course, whether that makes sense on a business logic perspective, but you do have that capability. What else we have? Retries, for example. What is a retry? A retry is basically an action that you wanted to perform failed, and now you want to simply perform it again without notifying the caller with an error. So why would you do this? Well, for example, if you have an external system where you know it's very flaky and unreliable, so without unnecessarily throwing errors to your caller, you simply say, oh, let's just try it again and tell nobody. So under the hood, you simply retry. The point with retries is it always has to be a conscious business decision. So not just retry just because you can, because if you don't know the implications of that, right? So for example, if you create an action at an external system and then you simply fire up that request again, you don't know whether that's, an item pointer call that you make to the external system, or, what's the implication of that for your business behavior. So always be aware that, what your retries do. So when I was in a project, we were building up a distributed system that was actually provisioning servers, like before the whole cloud. And we were in an environment where we knew that a lot of external backends were very unreliable. So basically, we built that in as a code, as a business logic, to say these and these and these actions have to be performed. And if they fail, then you can retry them individually so and so many times before you notify the support, and so on and so forth. And typically, you want to implement that on a code level as well, because what you then can do, you can here specify. So there's an add retry annotation, and then you can retry for so and so many times. And what you can do, that's also very interesting, there is a fallback annotation that also ships with microprofile fault tolerance. What you can do with that annotation, you can point this to another method that is executed as a fallback. So if any of these resiliency concept mechanisms fail with these exceptions, then automatically that will be called instead. So again, that needs to be a conscious decision. You need to know, okay, in this case, if it fails more than 3 times, then it will execute this code. Might or might not make sense, depends on what you're doing. Typically, this makes a lot of sense to include it on a code level, not only on an infrastructure level in case you communicate with an external resource. What else is there is circuit breakers. These are probably quite known. So circuit breaker basically tries to avoid to call any actions that are doomed to fail anyway, in order to prevent further damage, right? Very similar to circuit breakers in electrical engineering. And what that means on a code level, if we invoke an action that just fails with an exception, with an error, or even with a timeout that takes too long, and then the next so and so many times, after a while, we simply say, okay, we do not want to execute this anymore, because it's very likely that it just fails again, and we don't want to put overall pressure on the system or wait or execute it unnecessarily. So what we do, we specify a circuit breaker behavior on some functionality, where we go and say, try this for so and so many times, but if it fails more than 20 times, then just, give up and don't try it again. And then if you are being called again, simply fail with an error immediately. And then later on, you can, retry it again after some downtime. How do we implement that with plain Java Enterprise? Well, in plain Java EE, there is also not such a functionality. What we have in Java EE, who knows interceptors? That behavior? Probably a few of you, yeah. You can specify some interceptors where you can define some arbitrary behavior that can be invoked around your method invocation. Basically, you can then implement circuit breaker behaviors yourselves, by incrementing a counter and so on. But that's quite an effort, and we don't want to do that. So there is microprofile fault-tolerant circuit breakers, where you can go and specify a similar behavior by configuring, everything how your circuit breaker should behave. So for example, you could say you want to try for so and so many times. Per default, you can try for 20 invocations. You look at that window, and if more than 50% fail of these invocations, then this means it's failure, and then you have an open circuit. And then that means, it immediately fails if you call that method again. Then after a downtime, after per default 5 seconds, you can retry it once again. If it succeeds, that's good. Then it's closed again. Then it will work again. If it fails, then it's immediately open. So that's an also interesting thing to look at. From a business logic perspective, you might ask the question how much a circuit breaker might make sense, because it's a good, last resort behavior, but ideally these circuit breakers, of course, like in a house, should never trip, right? So ideally, you can mitigate errors maybe in another way, or in general, that should be a last resort. So for example, if you're in a distributed environment, you have multiple instances, and you might try another instance that you communicate with talking about retries, for example, but then a circuit breaker is a somewhat last resort for your functionality. Another thing that I want to quickly show you is a bulkhead pattern. What are bulkheads? Bulkheads come from ship construction, again, boats. So a bulkhead partitions a boat or a ship into multiple compartments that are isolated. And why? Well, in case you hit the iceberg and then the shell breaks and some water leaks in, then this means that only one bulkhead or few bulkheads will be destroyed and leaked with water, but the rest of the ship stays intact. So you still have a destroyed ship, but hopefully you can make it to the land, right? So if you think about the Titanic, for example, fun fact, or maybe not that funny, but the Titanic actually had bulkheads, the ship. But the problem was they were not really well tested and they were not high enough, or so they leaked, so, well, we know the end of the story. It still didn't work. So always properly test your, resiliency approaches. Bulkheads for applications mean, and this depends on the architecture of your system, that you typically partition the system into functionality that is somewhat cohesive, so that somewhat makes sense to put it together, and you isolate multiple functionalities from each other. So if one part of your system breaks, it doesn't affect the rest of your system. So if we talk about microservice architectures, well, that's quite simple. If you have independent service deployments, then they are, well, per default, per definition, independent. And if one fails, then it should hopefully not affect others. But if you are in a single application where you define multiple functionalities, maybe one part that's more important than another part, then you might think of this bulkhead behavior, and typically that means that you think about threading. So if you have, well, per default you have one thread pool in a Java Enterprise application, a single that comes from the request that is defined by the request thread pool if an HTTP request comes in, for example. And that means if your system now is overloaded with a lot of requests, then of course all of these requests come into that single pool and want to get the resources of that single pool. And that means if you have multiple functionalities, for example, one that is very important and the other one that might not be that important, then you still overload the whole system. So actually we see this here in our coffee shop application. If we look into the orders resource, so we have basically two functionalities here in my REST resource. One is please read the current coffee orders. Which orders do I have in the system? And the other one is please order a new coffee, right? Well, which one would be more important to go through? I would say the please order a new coffee. That's more important, because if the read fails, well, you can simply try again and try again and see whether your coffee is being prepared already. But if a customer orders a coffee, then you certainly want to have that order in the system, because otherwise you don't make money. For example, highly depends on what your business is. So in this case, what we do, or what implicitly happens, is that if we, let's start this barista again, if we would overload that system with a lot of requests, and want to at the same time read the coffee orders that are in the system and create new coffee orders, then we would actually overload all of that. Because per default, that Java Enterprise container specifies one request thread pool. And that one is being used, and if that one is overloaded, well, that's true for the whole application, if we talk about HTTP requests that come into the system. So if I, for example, want to order a new coffee, like this. New coffee, right? Works, 204, no content, that's good. And let's do something else down there. Let's just ask for coffees here. Oops. Get me the coffees. Now let's do this a little bit more. Like this. right? Here, new coffee, and there, new coffee, a little bit more. So on the top one, we ask, on the bottom one, we ask for new, for the current coffees in the system, and on the top one, we want to create a new coffee order, right? So that works, that's good. But now, in case the system becomes overloaded, and I have some nasty load test here that I can fire up, where I overload now my system, and then what you can see, that it becomes very slowly and even, stalls until the test is over, just because we now overload the system, and then, well, it doesn't work anymore. So what happens here under the hood is that, again, you have that single request thread pool, and that thread pool has also you define a single queue. So all the requests that go in need to, are waiting to be, handled. So it looks a little bit like this. You have, in this case, thread pool, that is all being there implicitly. So a thread pool with so and so many threads. And it's very similar to, a waiting queue for a checkout at a grocery store or at airport security. You have so and so many security folks working there, and a waiting queue. That queue also has an implicit length. And now, what happens is you just come in and you wait. And then out of the box, the behavior is just, we wait for so and so long until an implicit, timeout usually is being triggered, or until our request finally goes through, which is not the best behavior, because of two reasons. So first of all, we only have a single thread pool. So if anything any small functionality is being overloaded, that affects the whole system. And the second thing is, it's kind of unpredictable. So what we would like to do, if you now, again, think of the business side, ideally you specify some kind of SLA, service level agreement, that you want to guarantee that your user becomes a response in so and so many milliseconds, that your application is responsive. It might be the case that it throws an error, but in this case it's actually better to return an error immediately or quickly, rather than just taking a long time and blocking installing your user. So what we do instead is, first of all, we want to specify that behavior a little bit differently, of saying, okay, the queue is only so and so long, and if anything comes, if the queue is full and a new request comes in, we simply reject it immediately. That might be better, because then at least you get an answer immediately, or you will be served within your SLA time, within the service level agreement that you specify. And what we can implement there is back pressure, quote unquote, not in a reactive term, but in a sense that the server side simply can apply some pressure back by rejecting new requests that come in, and not overloading the system, especially the whole system. And in this case, we notify, quote unquote, by simply rejecting the request and immediately failing them. And the idea behind that is, if, for example, you want to guarantee a, let's say, SLA time of 200 milliseconds, and then, in this case, if I now come into my system and it takes a long time to handle that, then what happens is the client might run into a timeout anyway, and it also doesn't get a proper response, right? So you have an error, and I also consumed your whole SLA time, right? So it's much better to say, if you look at the current state in the system with the current queue capacity, then okay, I'm not going to make it to to respond to your request within 200 milliseconds. So it's actually better that I immediately reject your request, and you as a client might have time to, for example, go to another system and still be able to serve it within the SLA time. So talking about retries, or if you have a clustered environment. And that means we specify the behavior in that regard. Plus, talking about bulkheads, we can specify multiple of these with different SLA behavior for different functionality, and then not the whole system is being overloaded. How we calculate these queue sizes, mostly there is queuing theory and a thing called Little's law. And there's a formula behind that if you think about it, actually makes sense. Thinking about the processors, the threads that you have, the number of shops at your passport control at the airport, And the queue length, of course, the longer the queue, the longer, it will take until, you get through, you will be served in the worst case example if the queue is full. And of course, the more threads you have in the system, the shorter it will take. And of course, you have to regard the average transaction time, like how long does it usually take to answer that request. And then we can, specify that for your system to respond in time. So how we now implement that is, first of all, we want to make sure that we use multiple thread pools, and there is a capability that is called Manage Executor Service, defined in Java EE. So don't start your own threads, but you can use that executor service. In this case, well, actually, this would not help us much, because if we inject that executor service somewhere, well, you always have one, right? So then, well, say same problem. This doesn't help you much. And there's a way how to specify them in Java Enterprise. But luckily, there's also some third-party libraries. For example, Adam Bean's Porcupine extension. That is an extension for Java EE as well, where you can declare dedicated thread pools. And that means that you can specify a name for these thread pools here. So, for example, orders write and orders read. And this will be an executor service that is also managed, write executor. And that will be then used to, execute your code under the hood. So we specify two of them, a write executor and a read executor. And then what we do in this case, and this is now JAX-RS functionality, that we use asynchronous JAX-RS resources that do not use that single request thread pool that we just talked about, but basically, make other thread pools execute execute that logic that's being served here. So how that works is that we return a completion stage. In this is an asynchronous type. Here, instead of just a JSON array, it's a completion stage of a JSON array. And what we do, we wrap this into, for example, a completable future and say, please supply async this code. So that would work, but this is not the way how to do it, because if you know about a completable futures, this would use a JDK functionality to create new threads, which is also not the idea behind that. But what you want to do, you want to specify that executor once you create the functionality in your completable future. And now this will utilize that executor service under the hood. Same is true for give us the single coffee order. We do the same thing. Return completable futures, supply async from this one. And this one is a little bit more interesting to return to code. So we supply async this order coffee, and when that is compose, then apply, and once that is done, then we basically apply the response here, so we can return this. Or exceptionally, in case we have an error, then please do this and return the exception here instead. And then same story, supply async. What we do, we use the write executor here to tell which thread pool to use internally, and then we execute. Well, first of all, this order coffee, and if that if that succeeds successfully, then we return no content behavior, or exceptionally we say error, for example. So this is how we then would use these multiple thread pools using that library. What else we have to specify is a configurator. So executor configurator. This is what I would write here. There is configurator behavior that will be a CDI specialized. So this is how we can override some behavior here. Why? Well, we want to specify how these threat pools are being created, of course. So what I just told you with the queue size, threat pool size, and the behavior that we do. So we say there's also builder available. So first of all, we say abort policy. So in case there are few policies here, so how should we react to if this, if this pool becomes overloaded? Then in this case, we want to throw an error actually. This is the abort policy, and then we say, size, and now, just for the sake of the example, we say that is 4 and 4 in this case, and this is how we can specify it. So then what would happen, that we throw a rejected execution exception if the system or if that part becomes overloaded. And if we talk about how we return that to a client, then I said, well, we want to actually throw an error in this case. So what we do, we can specify a JAX-RS exception handler or exception mapper of that rejected execution exception. And then, in this case, we simply say, if we get that exception, well, then we want to have an HTTP response, in this case, status service unavailable, wherever that is, service unavailable, and we return that in this case. So that is, again, JAX-RS logic, how we map the exception to return it to the client. And then we can run it in that, like that, and we have defined 2 individual executor services that now serve this purpose. Now what we do, we want to rebuild the project and then run it, rerun it locally. So let's do this, and now we see that is currently being restarted. So that's still asking for coffee, and then hopefully once that is up and running, we have the same example, but once we overload a system, what we see, or once we overload, what the load test does, it actually requests a lot of read requests, a lot of gets for, well, actually this behavior. And then we see this uses a different executor than the please create some coffee behavior. So we expect that, the second one is still accepts everything successfully, but both are still responsive. So that's the whole point behind that. If I now fire up my load test, then what you will see, sometimes you get a 503 service unavailable. That is the case because now this functionality is totally under load. So in this case, these requests didn't make it through, but at least you have an immediate response. So in this case, this is better. Or, you have a successful response, or in any point, our please create the new coffee behavior that is still being responsive by specifying multiple of these bulkhead definitions. And that's one way how to do it. Actually, the latest version of microprofile fault tolerance also supports a similar thing using internal threat pooling, but in general, that is the principle behind that. All right, then a few other things in terms of threading. To sum it up, what to be aware of. Well, threats must be managed by the container. This is why we use a managed executor service or this Porcupine extension to create our threads under the hood. And we want to have a look into how we deal with these rejected executions. Rejected execution is basically once you overload the system and how does it react. So, does it just wait and you add it to the queue and then you wait for a long time? Or in this case, we reject after so and so many. And please regard HTTP request threat pools with JAX-RS or servlets out of the box. You always have a single request request pool. Then what else? In terms of Bulletproof Java Enterprise, well, we want to have a proper test harness or proper verification whether our application actually works. So what I said before about timeout behaviors, what you want to do, you want to test how your application actually reacts in these scenarios. So first of all, build up proper tests that executes all kind of things that would test for timeout behaviors, for example. Databases is a big one from experience, that, for example, your database goes down and comes back up again, then whether your application is able to reconnect properly, and so on and so forth, or how it reacts if you put a lot of pressure, if the application puts a lot of pressure on the database. Basically everything on a networking level that could go wrong, usually slow responses or faulty responses if something is unavailable, or just slow how you react to it. Data marshalling, that's another point, how you marshal data back and forth. There's this nice saying, be conservative in what you do and liberal in what you accept. So for example, if we talk about HTTP and especially hypermedia, so if we relate multiple HTTP resources and forward requests from one resource to the other, or if we enhance clients and communication with new versions, with new data, then in general you don't want to fail, you don't want to reject requests just because you're overly strict. For example, if you get more data than you would expect, right? If you get new unknown fields in certain objects, this should not mean that you have to immediately reject and avoid that request. So test that as well, how your application actually reacts to it. That's basically the takeaway of that. Then, if we look into cloud native world, what is also quite helpful actually in order to build up more resiliency is, first of all, how do we run our applications, especially if we run in Docker containers. Container orchestration, most of all Kubernetes, is a big topic, and thankfully that comes with a lot of resiliency being built in out of the box. So that means if we orchestrate our workloads to a Kubernetes cluster, then out of the box we have things like controllers inside Kubernetes deployments, if you're familiar with that, that make sure that we always have so and so much workload as desired in our system. So who of you is familiar with Kubernetes? Hands up. Oh, not that many. Who of you is familiar with Docker? Okay. So if you run Docker containers in a production environment or in general, it's quite easy to run them locally, on your laptop. But if you have a cluster of multiple nodes in your production environment, then that's another story. If you have to distribute, if you have to set up the whole networking stack and everything, so go to this node. Now deploy and run the Docker container and go to that node and then make sure they can communicate with each other. You get the idea. Everybody who has run that locally, that's quite some effort, and it becomes harder and with some networking and physical nodes involved. So this is why that technology makes a lot of sense to apply it in that way. And also, as I said, it, for example, has some so-called controllers in place. So if we look at how the YAML definition of our coffee shop application looks. So the first one, if you're not familiar with that, that's a service definition that basically is the logical abstraction of our coffee shop service. And the second one is a so-called deployment that manages these atomic workloads. And that means, in a nutshell, we want to have this Docker image that I just specified here twice. Please deploy this with 2 replicas somewhere in the cluster and make it accessible using this coffee shop service notation. So I quickly want to show you that. I actually have a Kubernetes cluster, not here on my laptop. You can either set it up locally, or what I do, I usually go to the cloud and use the managed Kubernetes cluster. Like the IBM cloud, you can deploy these very quickly, and then let's stop all these things. And then what you can do, well, you can take your kube control command line and just, go to your cluster and deploy new things, or, for example, ask for what is currently running. So a pod is this running workload, an abstraction over a container, and that basically runs your workload here. And one thing you can do, if I now go and say, oh, I'm very mean and I want to simply delete this pod just because I can, then what happens that your controller goes and immediately sees, well, you want to have 2, but I currently only have one, because that one has been deleted and that doesn't run anymore. So what happens is that immediately a new one gets created, as you could see here, and then starts up. So you always want to make sure that the target state is being provisioned. And if I now go against my cluster and say, well, same story, this is what you saw the whole time, that is still being available in this case. So that's one very tiny thing how cloud native technology can help you. Another thing is service meshes. So service meshes can enhance your applications with concerns that you might need in production. So for example, you can add resiliency in a service mesh environment without changing anything in your implementations, in your applications actually. And how that works, well, in a nutshell, is that in one of these running pods, or actually in each and every of these pods, you, instead of having only your main container, your application, you deploy two containers, so-called proxy container, so-called sidecar container pattern. They're always co-located. And then what happens, all of the communication, very similar to Java Enterprise or Spring proxies, will go through that proxy, right? And then, of course, that proxy has the full control over either, acquiring information of what you're currently sending, or of applying, different behavior. For example, applying resiliency. If your application, for example, would not implement proper timeout behavior, then these proxies could do that also and then throw a proper error. Or, they simply can define some retries or some outlier detections and a few other things. What is also very helpful, and this is a quick thing that I want to show you. So let's say this is now the definitions how Istio is configured, and this is very briefly, I know. If you're interested in that, at the end I'll provide you a link with some further resources how you can see what is happening there under the hood. But basically what you do, you specify all these, arrows in your diagram, all these routes that you have from one service to the other. This communicates with that one, and then you can annotate some more behavior. So for example, for this route, anything that comes into the system, please apply a timeout behavior. A timeout with 1 second, for example. And then, you apply this and you're good. So in my case, this means coffee shop deployment routing. I apply this behavior, and then we're good to go. So if I would go curl, and in this case again order some coffee, right, like I did before, but now I use my cluster version. I now do this with the timeout. But sorry. I should type properly. So this works, but also, the timeout was specified with the behavior of 1 second. So how do I test that, right? So apparently I just added a timeout, but I don't know, whether it works properly in this case. So what is also very helpful in this service mesh environment, specifically with Istio as the implementation, what you can do, since you have the full control over all these proxies, you can also, for test purposes, mess things up and include some errors, just for test purposes. But as I just told you, you want to test the resiliency of your application. So in a test environment, what you can do is, without changing other applications or without replacing other systems with mock servers, you can simply say, oh, this one should now be, slower, or just return an error, just because we can. So if we go into the other routing, the barista route from coffee shop to barista, and say, oh, by the way, for this route, please include some faulty behavior. For example, include some delay. And let's include a fixed delay of, let's say, 3 seconds, but not all the time, but only in 50% of the cases. Right? So what you do then is barista deployment routing. In this case, you actually introduce some errors on purpose. So that means that you would make this slower, that it takes 3 seconds. But as you can see, it doesn't take, 3 seconds, it actually takes 1 second, and then you get a timeout. And that timeout is now the timeout behavior from the service mesh, the 1 second that we specified on the very beginning, right? And even if you would not specify that on the service mesh level, then at some point the application, hopefully, has a timeout being built in and reacts in a different way. But in general, this is how you would test, or this is one way how you could test the resiliency behavior, by including timeouts or by including delays or faulty behavior. So this is what to say about service meshes. I can provide you some more resources if you're interested in that. That's an interesting technology also for resiliency. And they basically transparently add some cross-cutting concerns to your applications without changing them. For example, a lot of observability, resiliency behavior, some more complex traffic routing, and so on and so forth. And also some, test behavior, for example, making things worse for test purposes. So as a few key takeaways, we might want to consider these resiliency patterns that we have. Consider the threat pools, the implicit threat pools, what happens under the hood, and in general, no matter which technology you're using, always know what your implementation is doing under the hood, right? For example, talking about this pooling behavior. Then always test, and always test, for resiliency as well, and test the worst case scenarios, what will happen in production, in a production environment, and of course build in some observability, what's actually going on. And what's very important, you want to define and automate processes that you can do once something goes wrong, and where you can, analyze some behavior. So, for example, in this timeout example where your application was stalling, then have some process in place that goes into the cluster and asks the applications to have a threat dump or heap dump for memory automatically to get that, to analyze that out of band. So, know what's how you would react to it once something can go wrong. And that's basically all I have for now. So thanks a lot for your attention. You can use the first link to access some more resources. And we also have this, some more questions here. I can. Oh, perfect. All right. Soon, Spring Framework has an important role to develop microservices. What kind of property should be added to microprofile? That's a very good question. I would say the most important ones are actually have already been added. In my case, injectable configuration, health checks, microprofile fault tolerance. What else am I missing? Metrics, things like that. Basically, everything that's kind of where Java EE is lacking from a cloud native 12-factor application perspective, what you would need to include. So that's one thing. Another very powerful property where we're not there yet is reactive approaches, where you have to rethink a lot of things that typically how Java enterprise applications have worked, with a very synchronous model and the whole threat pool behavior. So that will require a little bit of rewriting. There are also already approaches, or like something happening in the microprofile area in that regard, but that's also a bigger one, but I think very interesting one for enterprise systems. Okay, there we go. What do you think about Java EE becoming Jakarta EE? I think that's a very interesting thing. In general, we hope that we have some more progress in the near future. It actually is also a very interesting story how microprofile will come into play then, because once we have something that could act as an incubator for new, soon-to-be standards, and with, interesting approaches, for example, like resiliency that we don't have there yet, or like reactive, we could use microprofile to try these things out on a more standardized, quote-unquote, level, and then, agree upon them and make them part of Jakarta EE. So I think that's a very interesting interesting happening. And in general, it's just, I think, positive that Java EE was moved to a foundation as compared to the past, and now it's Jakarta EE. And I personally like the name. Do you have any other questions in the audience besides these? After seeing? All right, then I hope this was helpful. And again, thank you very much
thank you, Sebastian,
for your attention.